Hello everyone, hope you're doing well. Welcome back to my channel. Today we are day 14 of the December daily LeetCode challenge. We are almost about to complete the half of this challenge, and we have just one question left to complete the half of the challenge. Today we are in day 14. It's a very good question. Let me tell you this. This is the kind of question that you can expect, in the level 1 rounds of any big companies. Okay, this is the one because there are multiple ways to solve this kind of questions. At the same time, there is so much for you to interpret and like there is so much opportunity for you to show your skills in this. So that is something that I want to tell you before starting this question. So if you have not tried this, or if you have already tried this and you are feeling like this is not something that I want, so let me tell this, this is the level which you have to prepare for. Okay, this is the exact level. And at the same time you have to be very vocal about what you are seeing, because see, there are a lot of things to interpret here. Okay, so this kind of questions, first understand what they expected, explain the same to interviewer. Only when they agree that yeah, what you're saying is exactly the one they are expecting, then begin with the question. Okay, that is something that I want to tell you before starting this question. So let us begin today's question. We'll be seeing actually two approaches. One will be analog and approach, the other will be OFN approach. Okay, we'll see both of them. So coming to this question, basically, you are given a zero index integer. If you see here, they are given just only one array as the input. Okay, where nothing else here. So you are given a zero index array nums. A subarray of nums is called continuous. See, this whole question is about a subarrays which are continuous. Okay, so please pay attention to the definition they are saying for a continuous subarray. A subarray of nums is called continuous if, see, the idea, see, you can go through this part on your own, but the idea here is, see, if a subarray, the idea here is take a subarray, t- the difference between the max element and the min element in that subarray, if it is, less than equal to 2, then that is a valid subarray. Okay, as simple as that. Then you can call that as the continuous subarray. Okay, and finally you have to return the total number of continuous subarrays. Okay, I hope you are getting the question. See, it is very simple. Take all the subarrays. A subarray is called continuous if, see, please don't go by the literal meaning of the word continuous. Okay, they have used a different meaning here. Okay, the subarray is called continuous if. So see, don't go by the literal meaning of the word continuous. A continuity has a different meaning here. Okay, so you have to change your what you already know about continuous subarrays. Just try to think of it as that saying, giving it a due name. Okay, simple as that. You have to count basically. See, question first of all is count a particular type of subarrays. Okay, that is the question. So the idea here is take all the subarrays and you will have to count among them the ones for which, if you subtract the max element and the min element in that particular subarray, the difference should be less than equal to 2. That is what they're trying to convey. Okay, you have to count all such subarrays in the given array for which the max element and the min element difference is less than equal to 2. Okay, I hope you now understood the question is very very simple. Don't go by these things, they are trying to confuse you, but the question is very simple. Each subarray, take the max element, take the min element. If the max element minus min element is less than equal to 2, you'll have to consider that as subarray, and like you have to count that as your, you have to count that in your answer, something like that. Okay, then they're trying to give you the definition there. One important thing here is they are saying you should not take the non-empty ones. Okay, that is something important. So please take this also in your calculations. If you're using any ready-made formulas, so please be aware of this thing, that you should not count the non-empty ones. Okay, as simple as that. And I hope you are aware of what a subarray is and how it is different from a subsequence. So I'm not going to in detail of that. Okay, because that is not required in this question. So the question is very simple. We'll see the example one. First of all, what is happening? See what is happening. If you see this part, the idea here is if you take this particular subarray, okay, wherever 5 and 2 are present together, that subarray will not be possible. Okay, because if you see 5 is going to the max element, 2 is going to the min element. 5 minus 2 is 3, which is not less than equal to 2. Okay, that is crossing the limit. So such kind of subarray we should not take. So any subarray that has 5 and 2 both will not be counted. Other than that, everything else will be counted. Okay, so if you see, first of all the single ones are counted. Okay, they are showing you all the single ones, and then among the double ones they are showing you these things, and among the triple ones they are trying to avoid the 542 combination. Other than the 542 combination, the other combination of size 3 is 4 to 4. They're taking that, and obviously we cannot take the size 4 because 5 and 2 will be together in that. So these are going to be the sums, these are going to be the subarrays. You have to return their count, as simple as that. Okay, so that is going to be the answer. If you see the constraints here, constraint, the number is going to be always positive. That is one good thing here. And other than that, yeah, the length is going to be 10 by 5, which is typically the range that we expect in a medium level question. Let us begin the thought process now. See, idea is going to be very simple. We will consider all the subarrays. Okay, and among those subarrays, which for whichever thing the maximum minus minimum is less than equal to 2, we will consider them. Okay, that is the basic idea. So before proceeding, just I want to tell you something. See, the idea here is we will be doing only single iteration in the array, so we will not be using two for loops to go through each to get each kind of subarray. Not like that. I will not be doing that. So see the approach here. See, for example, let us say I am taking this for now. Okay, this is going to be my, this is my target. Okay, that is, I'm going to consider this is going to be my point of focus. So this is the this part, right? This is the part. Now So the L is 1 and R is 3 here. Okay, so basically I'm trying to do a single window approach, that is sliding window approach, and in that whenever you're using a sliding window, you have to have two pointers. Okay, the starting part and the ending part. So in this case, let us consider the index 1 as the starting part and index 3 as the ending part. Okay, so this is the array that I'm considering. There is a subarray that I'm considering. Now if you see, the max element is 4 and the minimum element is 2. 4 minus 2 is definitely less than or equal to 2. Okay, 4 minus 2 is less than equal to 2. That is fine there. Okay, that means this is the valid one. Now I need to know all the subarrays that are there in part of this. Okay, so how many subarrays you can form a part of this? Okay, let us see. First of all, 4 to 4. Then this itself is like a subarray, right? This itself in itself is a subarray, right? As simple as that. Next, you can have 2 comma 4. Okay, as simple as that. Then you can have this particular 4. Okay, so the idea here is, when I'm taking this combination, see, now you will be saying why 4 and 2 is not present here. Okay, like, see, the idea here is 4 and 2 will be processed when I was doing that. Okay, currently, see, 4 and 2 will be processed first, then we'll come to the other 4. Okay, so currently we have processed till here, till this point. Okay, so that is the basic idea. Remember that. So for that reason, now when I'm at this particular position, I'm just trying to explain how this formula is coming. Okay, as simple as that. If you already know, you can skip this part. If you don't know, you can be with me and just try to understand what is happening. See, idea here is, whichever array is ending in the last element, say this is going to be the last element, right? We'll have to find out all the subarrays that are ending in this element. Okay, so how are they? First of all, this overall itself is ending at the last element. Then that this particular thing is also ending at the last element, so this is the one. And other than that, the last element in itself is ending here. Okay, so this is the one. So these are going to be the three continuous subarrays. If this whole, that is, if you take and subtract the maximum minus minimum, if this is less than or equal to 2, then you can consider all the subarrays that are ending that particular point to be your valid answers. Okay, so how to get this number? That is, see, here we are getting three such subarrays. So how to get this number 3? The idea is you can do r minus l plus 1. Okay, so if you do that, you will get 3 minus 1 plus 1. Okay, which is equal to 3. So this is the calculation that we are going to use. Now the question you will ask me is, why 4 comma 2 is not included in this? So see, the idea here is, when I am at 2, that time I would have done that processing. Okay, currently I passed that 2 and I'm currently at this particular 4. Okay, so as simple as that. That is the reason why that particular thing is not included in this. That would have been processed in the previous iteration itself. Okay, as simple as that. Now let us quickly see the approach. See, this solution that I'm going to show you currently is, I'm going to show you using the min heap first. Okay, then we'll go by the double-sided queue solution. So idea here is very simple. What will happen is, see, you will, okay, let me do the tracing first and show you to you how this works. Okay, see, first I'm doing the tracing for the example one. See here, first I will be including 5. Okay, then after after adding each thing, I will be checking whether it is crossing the limit or not. Okay, this is going to be my algorithm. See here, I will first of all include them. See, I will be maintaining. Okay, let me zoom out first. I am basically maintaining two heaps. Okay, one is to get the minimum element, other one is to get the max element. Okay, as simple as that. And for getting the max element, okay, I will come to the details of it. Why I'm adding minus and all. We'll come to the details of it later on. But just try to understand this fact that we are having two arrays. That is two heaps here. One is to get the minimum element. One is to get the maximum element. Okay, as simple as that. So at each number, we'll be pushing them into the heap, and then we'll be checking whether they are satisfying the property or not. Okay, whether the max minus min is less than equal to 2 or not. Okay, if that is not the case, then what we'll have to do, we will have to start shrinking the window. Okay, as simple as that. So let us quickly see how this works for the example number 1. So first I am putting the element here. Okay, 5. Now I will do, see, you cannot with a single element, obviously you cannot do that, right? You cannot do max minus 1 and all. Obviously this will be always 0, max minus 1 will be 0 in this case. Okay, so this is a valid element, fine. So I will expand my window next. Okay, and then I am including 4. Now the max and the min. Okay, 5 and 4 are the max and the min. If you subtract them, you are getting 1, which is well within this. Okay, so again this is fine. Okay, okay, let me show the answer also here so that you can get a better understanding. So initially we had only one element, 5, so the answer in this case is 1. Okay, next we have included 4 also. 4 is also valid, like this max minus is still less than equal to 2. So I will include 2 more points to the answer. Okay, answer will look like this now. Fine. Next we will include 2. The second I include 2, what will happen is, see, the max minus min, which in this case is 5 minus 2, which is 3, which is not less than equal to 2. So this is not possible basically. Okay, so what I have to do, I will start shrinking the window. So what I will do, I will remove this particular element first. The first element should be removed first. Okay, now 4 comma 2 remains. Okay, 4 comma 2 remains. Obviously this is a valid solution. Okay, so in this case again I will have 2 to answer. How I'm getting this 2 I'm getting from this particular calculation. Okay, this particular calculation I have added 2 to the answer. Now next the last 4 comes, so this particular 4 will be added to my window. Okay, again, like, this is a valid one. 4 minus 2 is fine, so again I will include 2. So this is basically how my answer is going to look like. Okay, 607. And okay, just a second, I am missing something here. Just a second, let me. So see, when idea here is, see, it is first 3, okay, then 5, and then 8. Okay, that is how they are getting it. So in our case, okay, it became 3, and then 5, and then okay, the last one basically it has to be 3. That's what I was missing. See, it is a length 3, right? So this last one will be 3. So if you see this now, this is basically 5, 6, 7, 8. Now we are getting the correct answer, which is 8. Fine. So this is going to be the actual calculation. I have shown you the diagram of the the sliding window that I'm using. Okay. So you see, the idea here is in the first approach, but I'm starting from index 1 till n minus 1. Okay. So the index 0 I'm processing before itself. Okay. So this is the element. Okay, that I'm going to insert in my heap. So what is this element? The first part is the number itself. The second part is the index. Why I need to do the in the index insertion? Because see, when I am tracking my window, that is when I'm contracting my window, I will have to remove all the elements which are not in the window. Okay, as simple as that. For that reason, need the index. Okay, that's the idea here is when I do l plus 1, I need to remove all the elements which are now no more in my window. Okay, from the heap. For that reason, we need the index also. And since you if you see my video, you'll already knowing this, that the heap implementation in heap collabor in Python is actually a min heap. So if you have to simulate a max heap, you'll have to add a minus sign here. So whenever you're using this, you have to add a minus sign while pushing also and while popping also. Okay, as simple as that. Fine. Then L and R both are 0 currently, and we are starting now. Now R is equal to, see, this R you can basically remove from here. This is not needed because R is going to be from here. Okay, R is going to be the iteration variable here. Okay, it's starting from 1 till n minus 1. So that what we are doing, see, first of all, we are pushing that element in our both the heaps. Okay, the min heap also and the max heap also. Okay, while pushing the max heap, you have to insert a minus, and that is something. Okay, fine. Then what you have to do, see, then I'm going to do this calculation. Okay, then I'm going to do the absolute value of the max heap value, that is the max value minus the min value. Okay, if it is greater than or equal to 2, first of all, see the implementation here. Whenever you are taking the max heap value, you have to first of all have a minus sign. That is obvious. Next thing is min heap. Since this is supposed to be the minimum value, you have to subtract that, so that's why the minus sign is here. Okay, now I'm taking the absolute value. Why I'm taking the absolute value? Because in the question, if you see, they are also taking the absolute value basically. Okay, this is the absolute value. Okay, so I'm taking the absolute value. Now if this is greater than or equal to 2, okay, what I have to do, if this is greater than or equal to 2, that means the max and min are somewhere having a difference greater than or equal to 2. In that reason, I will have to start shrinking my window. How to shrink my window? That for that reason, I will have to move the L pointer now. Till now, if you see, we are moving the R pointer. Now we'll have to start moving the L pointer. How to do that? So first of all, I will check this value will run. Okay, see, if this condition is true, I am going to run this particular value. This value will do all the things for me. How does it doing? Let us see. First of all, it is checking whether there are some elements in the min heap, there are some elements in the max heap. If that is the case, and till this particular subtraction, that this is subtraction, right? If the subtraction is still greater than or equal to 2, if that is the case, this value will keep continuing. Okay, what is we are doing here? First of all, we are doing L plus 1, L is equal to L plus 1. Okay, that is we are moving the pointer one side. Okay, by 1 unit. Okay, as simple as that, from the left hand. Then I'm checking after moving the pointer if the top element, that is the minimum most element in my min heap, if that the index for that element is less than or equal to 12. That is that particular element, it is outside my window now. Okay. For that reason, I will have to pop that window out if that is the case. Okay. What I'm checking, go to the element which is being there in the top of the heap. Okay, which is the root of the heap. That is, it is the minimum element. Remember that. If that element is less than or equal to L, we'll have to remove that. Okay. Similarly, for maxive also, you have to do the same thing. Okay. For maxive also, try to do the same thing. If that is okay less than or equal to L, simply remove it. Okay. Remember one thing, you will ask me, see, you are using minus sign here, then why you are not using the minus sign in the calculation of the maxive here? Remember, the minus sign is coming for the number only and not for the index. Okay, remember that part. The index is in the second, this is the second parameter of the element, each element. Okay, so index is not having minus sign here. For that reason, when I am checking, so remember, I am checking the index here, that is the 0 comma 1. If you see here, this is the 1 is representing the index. Okay, this element. Okay, for that reason, I am not using any minus sign and all here. Okay, because that the index is stored as it is. Okay, it's not stored with a minus sign. So for that reason, if the max element also, if it is outside the current window, then you have to remove that also. You have to keep popping the element. This value will continue till either both the heaps are empty, or this condition started becoming false, or like all the elements that are removed from the window are removed from the heap also. Okay, simple as that. This value will run till then. After we are coming out of this, we are using this particular calculations. What is this calculation? I've already shown you here. Okay, this calculation I've already shown you here. Okay, so I'm not going to do in details of it, but yeah, this is how it is coming. At each loop, we are going to calculate that. Okay, and remember, this calculation should happen only after ensuring that these conditions are true. If these conditions are not true, we are going inside the, that is, we are starting a while loop and we are trying to ensure this. Okay, as simple as that. Fine. After we come out of it, we are just printing this printing part is just for you. While you segment, just comment this part out. Okay, and then you are showing it. Okay, let me show the output of this first. So if you see here for the example number 1, what is happening? First of all, it is going till 5. See, we are starting in the index 1 and we are adding the index, that is C. Remember 5 is already there in this loop that I showed is starting from index number 1. So 4 is included. The count currently is 3. Okay. Remember one thing that I did not show you is that the count is starting from 1. Okay. Why? Because I'm not starting with the 0th element. You see, I'm starting with the first element. For that reason, the count is starting from index, yeah, value 1. Okay. As simple as that. So if 4 got included, then 2 got included. When we're including 2, we'll have to remove 5. Okay, as simple as that. Because of that value, it got removed. So the value here is 2. That is the length of this is 2. The length is 2. That means the 2 will be added to the previous answer. So 3 plus 2 will happen. So it becomes 5. Okay, as simple as that. It became 5. Next, we are the last element 4 is getting added. So this is the current window now, 4 to 4, and we are done. For that reason, the length is 3. So 3 will be added to the previous count, which is 5. So 3 plus 5 will be 8. And 8 is going to be the final answer here. Okay, as simple as that. So this was first approach. And if you talk about the space and time complexity of it, see, we are maintaining two hoops which are going to store at max of n elements. For that reason, the space complexity on a higher limit is going to be O of n. Okay, as simple as that. Fine. Now coming to the time complexity, see, time complexity part is going to play a very important role. See, this particular while loop, this particular for loop is going to take O of n time. Okay. Other than that, see, I'm not going to in details of why this while loop and all I'm doing. See, I'm not going to see in that way. Okay. So the idea is very simple. See, when I'm using the heaps, the idea here is each element will be popped only once, at most once, and each element will be pushed. See, each element will be pushed and popped at most once in both of the heaps. Okay. So I'm not going to talk about this while loops and all. Okay. I'm talking about the ideology that I'm going to implement. Okay. Similar that if you see there are multiple while loops here, but I'm not going to talk about in that reference. The idea is very simple here. See, my implementation, if you see, this particular for loop has O of n complexity. Now, in each iteration, what I'm doing, I'm not going to talk about that. But the ideology here is that I am having two heaps, and in each of these heap, each element will be pushed and popped at most once. So if you talk in that sense, the idea is going to be at max, it is going to take n log n time. Okay. So the overall time complexity, if you see, it is going to be n plus n log n. Okay. But since n log n is the dominating factor, we will remove the n and it will remain n log n only. Okay. That is going to be the time complexity. And space complexity, why it is often, I've already explained because of the heaps that we are using. Okay. Fine. So this was the first solution. I have already submitted this. This also works very fine. Now we'll try to do a further more optimization. Okay. The other optimization that we can do is it's going to be the DQ approach. Okay. Why the DQ is relevant here, I will show you that. Okay. So we'll have to consider example first to understand why it is important and why the heap was not able to do this. So see the case here. See the case here, like let us say this is my nums. Okay, this is going to be the example one nums. Okay, let us say my min q. Okay, like this is going to the equivalent of the min heap. Okay, let us say at some point it is showing like this. Okay, 5 comma 4 it is showing that. Then we are about to add the next element, which is 2 here. Okay, now once I add 2 in a heap, what will happen? 5 and 4 will remain, and 2, like these three elements now will be there. Okay, after I add 2. But what we are trying to do is, remember, the more elements you have in your heap, the more the time conversion will be when we are adding a element. Okay, that is, the pushing and popping is going to take log n times, where n is the current number of elements. Okay, for that reason, the more elements you have, the more the complexity will be, as simple as that. Okay, but let us logically understand what is the relevance here. I am having 5 and 4 in my heap or whichever place it is. Now I'm going to add 2. But once I add 2, let us, I'm talking about only the min, that is the minimum part. See, once I add 2, I know that 5 and 4 are of no relevance here. Why? See, once I added 2, there is no need to bother at 5 and 4, right? Because 2 is going to be the smallest among them. Okay, so 5 and 4 can be removed at all, like they can be removed from the calculation itself, because they are left of current element. That is, we are not going to visit this 5 and 4 again. Okay, as simple as that. Once we have a smaller element, which is 2 in this case, 5 and 4 are not relevant to us. Okay, so you have to see here, after adding the 2, what we are going to do, we are only going to store 2. Okay, and we are going to store 2. We will not store 5 and 4. Why? See, the idea here is, once you are inserting an element in your current queue. Okay, in this solution, what I'm going to do is, when we are inserting element, let us say in the min queue, what I will just ensure is that if there is any element, okay, which is greater than 2, that two elements will be removed. Okay, as simple as that. That is, any element which is greater than the current element which is going to be inserted, you should remove those elements. For example, current element is 2. So while before inserting that, what are all elements which are greater than 2? I have to remove them. Okay, so if 5 and 4 will be removed, then 2 will be inserted. Similarly, when we are going to insert this last element 4, what we have to do? Same thing. Any element that is greater than or equal to 4 should be removed. Okay, so since 2 is not greater than or equal to 4, 2 will be retained. Then 4 will come. Okay, as simple as that. So this is going to be the approach that we are going to use here. Okay, because see, why I'm talking about this approach is that, see, if you see here, we are trying to save much complexity here, because we are certainly removing certain elements which are of no use to us, but in the previous solution we are not doing that. Okay, so we are doing this in this approach. And one more advantage that we are having is, see, we are going to use the DQ. What is DQ? Basically, DQ is the double sided queue. So the advantage that we get here is, for example, let us say we're using the append operation. Append is going to do at the end of the array, okay? So that is going to O of one time. But let us say you are going to append something in your zeroth place, okay, zeroth index. So that will not take O of one time. Remember that. That will take more than that, because the pointers will have to go there and then they will have to insert and so on, okay? For that reason. But the advantage about the double-sided queue is that you can do both append and pop operations at O of one time from both ends, okay? That's why it's called a double-sided queue. That is the advantage of this, okay? So we'll be using this for this approach, okay? That is when, see, in the heap I have simply, if you see in the heap what I'm doing, I am simply pushing the elements, okay, as it is. Okay, then if they are not satisfying this property, then I'm thinking about removing certain elements, okay? But here we'll not do that. Every time, like, see, the calculation that is if they're satisfying the absolute difference or not, that will come later on. But while inserting itself, what I will do is, for example, I'm going to insert 2, then I will ensure that any element that is greater than or equal to should be removed in the min queue, and in a similar way for the max queue also, okay? So let us see the solution. These are the two queues like the previous solution. The rest all remains the same here. Yeah, here I'm going to start the count from 0, because it was here the for loop, that is a variable r, is going to start from 0 to n minus 1. Okay, unlike the previous approach where I was starting them from index number 1. Here it will start from index number 0 only. Okay, as simple as that. Now what I'm going to do, see, before inserting this particular value, okay, before appending, see, if you see in the min heap, I'm going to append the current, if you see current value, okay, and then its index. See, the element structure remains the same as the last solution, but the idea is, once before I inserting, what I have to do, see, I'm talking about the min queue, okay, so it is going to show the minimum value. So what I have to do, any element that is greater than the current element, okay, any element that is greater than the current element. Remember why I'm writing -1 here, because I'm starting from the last. That is, see, normally what will happen, see, this is the queue, right? So what I will do, I will start from this fourth, this zero fourth element on it. That is the last element that is there in my heap currently, okay, in my queue currently. So I'm going to target that. So I'm taking the -1, okay. I'm checking if it is greater than equal to my current element or not. If it is greater than, I'm simply removing it, okay. As simple as that. I'm simply removing it. And since, remember, if you have to pop from the left, then you have to use the pop left function. If you have to pop from the right, you can simply use the pop function, okay. Then I'm inserting this particular element. Same is the case here for the other one. This going to the max queue. So I'm checking if they're less than that. Okay, any number is less than that, then it's of no use. So I'm popping it out before appending the current element to the queue. Okay, simple like that. And then I'm just checking. See, this part is pretty much the same as like the last solution. If they are not following this condition, then we'll have to do the that we have to start contracting the window, okay, because this is a sliding window approach. So this is the same as like exactly like the previous solution, okay. It's exactly the same as the previous solution. We are doing l+1 and we are like popping the elements out, okay, if their index is less than the current element, okay, as simple as that. And fine, like this is exactly same as the last solution, and this all rest of things are exactly same, okay. So this is the only difference. If you talk about the space and time components of this, space component is going to remain the same because we are using two queues here. Previously we were using two heaps, but the time complexity is very different here. Why? See, again, same thing. We are using a for loop here. Okay, that's going to take off and time. But other than that, like, see, I'm not going to deal with this values and all. I'm just going to tell you the ideology that we're using. Okay, because if you start seeing this values, your calculation will be very difficult to get the time of it. Okay, so the idea here is, see, each element in the queue will be pushed and popped only once. Okay, that's at each element. Okay, we are having n elements. Out of them, all the elements, there is a possibility that they will be pushed at most once and popped at most once. Okay, so you see in that way, since this pushing and popping operations are going to take off one time because it is a DQ, for that reason it is going to be O of n solution. Okay, for that reason C is going to O of n solution. O of n for the this particular loop, and O of n for pushing and popping out n elements. So both are taking O n time, so it's on overall O of n solution. Okay, as simple as that. So the time comes to be O of n. See, often that was all for this video. I hope you like the solution. See, this is a really good question. See, there are multiple ways to do it. Some of you may also be trying some other approaches that will also work here, because after all, you have to just ensure, see, because analog and solution will also work. Okay, you can try anything. You can even try sorting and other stuff also if you want. You can try that also. I'm not doing that because see, ultimately idea is anything that is analog and will also work. Okay, simple as that. You can try those things also. That there is definitely a way to get in using those approaches also. You can try multiple, but I just showed you two which are relevant. Especially the first one is something which is very relevant, but yeah, it is slightly costly in the terms of complexity. There is a DQ solution which is more efficient than that. Okay, so often that was all for this video. See, like this question, it comes in interview. The first thing that you have to do is, see, to get this kind of formulas. First of all, you should get some hint from the interviewer. Okay, you have to get this kind of hint, because without the hint, it will not be possible. See, what will happen here is, in the interview itself, they will give you example and they will give you this kind of formulas directly. Okay, that for each iteration, if you do this, you will get the uh, the pattern here. Like these formulas mostly will be given in the question description itself, in the example itself. Okay, LeetCode doesn't give them, but what will normally happen is they will give this kind of solutions in the example that they have. Okay, they would have already prepared this, so you'll have to utilize them and you have to frame the answer. Okay, other than this, you will not get much hints here. Rest of the things you have to do. But yeah, if you're getting stuck, definitely you can expect hints. But like the solution, like that decisions to choose a min heap, use a DQ, these things should come from your side only. Remember that. What elements you have to check, what structure your solution should be, what all you should store here. See the reason to store index, that is very crucial. Like if you're not doing that, let me tell you, this will be very big disadvantage. Like it will seen as a big disadvantage in a solution. Okay? If you're not showing the index, for example, when you're moving the window, right, we have to ensure that whatever elements that you have currently, among them which are not in the window should be removed. Okay, in the heaps, whichever elements are not in the window currently should be removed. So to ensure that you are able to do that, you have to store each element with its index. So that is a very crucial decision to do that. Okay, if you're not doing that, they will consider that you have not read the question correctly, or like your solution, you're not analyzing everything before coding the solution. So please don't do this kind of mistakes. I can give these two solutions to you. Please go and practice thoroughly. See, remember that it doesn't matter how much you are failing in your practice sessions, but it will matter if you're doing a mistake in your live interview. Remember that. So fail as much as you can in your practice, but those you'll have to learn something from your like failures, so that you don't repeat them in your real live interview. This is a really good question. You can, like, if you're able to solve this kind of questions. See, I'm not saying like which, like, you should come with the directly the double-sided queue approach. I'm not saying that. At least you should be able to solve them using the heap, because like if you see currently last multiple days, like last whole week, we are getting multiple questions on heap. So I'm expecting that you should at least be able to solve this by using the heap now. Like once you are able to do that using heap, like yeah, you can like learn about this DQ. Like I guess in the December daily code challenge, this is the first time we are getting a question on DQ. So I understand that if you are not aware of this, like just try to learn it. This is also very helpful. Double-sided queue is very helpful when you have to like push and pop up. You have to push and pop elements from either side of the queue. That is zeroth index and the last index. Remember that. For that reason, it is very helpful because it will give you O of n of one time complexity. If you see here, we are popping here from the right. Okay, we are popping from the right here, and if you see here, we are popping from the left here. Okay, so that is the reason why these are going to be very very helpful here. Okay, remember in a normal like any normal list or array, if you do this, this will not be open anymore. Okay, you cannot do like pop from both the ends with O of one time. Remember that if you're not using a DQ, that is the reason why DQ is a special data structure that is built for this reason only. Okay, as simple as that. So yeah, friend, that was all for this video. If you like my efforts, if you learn anything new from my channel, please do subscribe. It really gives a lot of motivation to continue further. My aim is to deliver quality content to all of you at the same time. This is helping me also to maintain my streak. Currently, I've solved 53 questions. Like this is a streak that I'm maintaining. I want to do much more. I want to give you much more, quality content. Please do support me. Please do subscribe to my channel. This really gives a lot of motivation to continue further. See you tomorrow. Thanks a lot.